Our last speaker, Rungang Han, and he's going to talk something about tensor block model.
Okay, thank you, Yushin, for the nice introduction. It's my great honor to receive this award, and I really appreciate this wonderful opportunity for presenting my work here, although I cannot make it in person because of my visa problem. And today I'd like to discuss the multi-way clustering problem in tensor block model. And this is a joint work with Dr. Yuetian Luo, Dr. Miaoyan Wang, Dr. Andrew Zhang when I was a PhD student at the University of Wisconsin-Madison. And this work is actually motivated by a class of two-way clustering problems in high-dimensional statistics, where we find that in many scenarios, the data matrix usually has some natural block structure. One popular example is a network analysis, where we want to infer the network community structure from observed connections, which is usually represented as some adjacency matrix. And more generally, we can also extend this idea for general bi-clustering model, where we observe some P1 by P2 response matrix, such that it can characterize a response with heterogeneous rows and columns. For example, in the right panel, we have this example from the single-cell RNA analysis, where we have the gene expression matrix from different genes at different rows and different cell lines at different columns. And it is interesting to analyze this kind of data by identifying this block structure so that we can better understand what's the differential gene co-expression pattern. And in general, the two-way clustering aims at target that trying to identify this marginal clustering for row and columns index from the matrix data. And we also found that the similar idea can be extended to even high order data, namely the tensor. For example, we can start from the multi-layer network. That being said, instead of just considering one adjacent matrix or one network, we can construct n binary tensors to characterize the relationship or the connections for the same node set under different contexts. As an illustration, in the left panel, I give this plot for this European air route network. In each slice, it corresponds a particular airline. And within one slice, we connect two particular nodes, which represent different cities if there is some flight operated by this particular airline. And we can also extend this idea from bi-clustering model to tri-clustering model, where we have this P1 by P2 by P3 response tensor. And this has many supportive applications and motivations in biological study. For example, in the right panel, we have the microbiome study data, where each slice represents a microbiome measurements at different human body part, for example, skin and gut. And within one slice, we have a lot of columns representing different patients or subjects with potentially different phenotypes. And this color within one column represents the relative composition of different microbiome. And it is interesting to explore the group or clustering structure along different directions. So for all these kinds of model and data, our question is, what method should we apply and what theory can we obtain for this kind of multi-way clustering when we have this tensor data? So in this talk, I will first introduce this general tensor block model. And we will assume that we observe a tensor data Y, which is an order D tensor with dimension P1 up to PD. And we'll assume that it has two critical components. The first component is the block mean or clustering structure, which is a smaller tensor, but with the same order D, with dimension R1 up to RD. Here, Rk is actually the number of clusters we impose for each direction. And we have this Zk, which represents the marginal clustering membership. Given this S and Zk, we can determine the entry of Y according to its corresponding index and the corresponding membership it belongs to, and the block mean. And then we add some independent mean zero random noise to observe, to model the statistical error. And using some tensor algebra, we can actually represent this model in a more compact way by the tensor matrix product. And I will not bother you with the exact mathematical definition of this tensor matrix product, but you just need to know that here we have this Y as a huge tensor and S is a block tensor, and we introduce this M1 up to MD as a membership matrix, which has this kind of relationship between this MK and this ZK. So our target is to try to estimate the marginal clustering ZK label up to some permutation, and this is a pictorial illustration. We have this block tensor as our population, which we want to estimate, and it can be decomposed as this kind of Tucker decomposition with this M as the block membership. But what we really observe is the permutation of this row tensor under some noise, and the high order clustering aims at the recovering from the left to the right. And for simplicity, I just want to note that when D equals to 2, the previous algebra and the model just reduce it to the stochastic block model, which is a very popular one, which that are widely studied in network analysis. So to start with, we may want to think, okay, let's just start with a basic model. We're assuming that, okay, the noise are ID Gaussian. Then at first glance, we may just want to seek to find the maximal likelihood estimator, which has this simply form. And actually it has been proved by previous work of Wang and Zheng in 2019 that this MLE already achieves optimality, which I will define and discuss later. But the question is that this programming, although it has a square laws, it is optimized over a very complex region where we have S as a continuous variable and the multiple ZK a discrete variable. This is a mixed integer programming, and in general, the calculation is NP hard. That being said, although MLE is statistical optimal, it is difficult to calculate in practice. So in this work, we propose a two-stage estimation procedure, which is real efficient in terms of calculation. So we have two components. The first component is still to try to optimize the likelihood, and we propose an alternating minimization algorithm. And the second component is that we provide some warm initialization, because as I just mentioned, the objective is non-convex and mixed integer programming. That means even I can find a local optimization procedure, I cannot guarantee it converts to the MLE. So I still need some warm initialization, which makes sure that the local optimization algorithms work. And this warm initialization can be taken as a tensor style of spectral method, which will be discussed shortly. So before I discuss the local optimization strategy, let me first do a brief review on K-means and Lloyd algorithm. So typically in multivariate analysis, if we want to cluster n samples in a p-dimensional Euclidean space, typically we will want to solve this following K-means programming. And the most practical way to do that is to apply Lloyd algorithm, which we estimate the labels and the centers alternatively. The similar idea can be used in our setting. Recall this is our object function, which is a negative log likelihood. And we observe that although we have d+1 independent arguments to be optimized, as long as d of them are fixed, the rest one can be simply optimized. Specifically, if we know all the clustering labels along all tensor modes, we can simply update the block mean as an average after we assign the entries to different membership. And if we know the block mean S as well as arbitrary d-1 labels, the rest one can be updated by performing the nearest neighbor search, which minimizes this loss conditioning on the other fixed parameters. And we can do these two procedures iteratively, and we can make sure in each step this loss function will get decreasing. And we call this as a high order Lloyd algorithm which serves as our local optimization procedure. And also, as I just mentioned, even we have a decreasing method for the objective function, we can still not guarantee it converts to MLE because the programming is non-convex. So it's essential to make sure we have a warm initialization for the high order Lloyd algorithm to succeed in statistics. And usually we apply spectral method when we are doing some data analysis for matrix model. And essentially by spectral method, we can actually calculate two singular subspace U1 hat and U2 hat S, which actually maximize this kind of projection values. But the similar idea does not directly apply to tensor, because if we similarly write down the same object, we will still find that this programming is NP hard. It's not like matrix, you can just do the SVD. This programming is NP hard in general. And as a surrogate, we just want to find some efficient approximation of this UD hat S. And this comes to our idea of high order spectral initialization. Recall that the expectation of our observation Y tensor can be written as this tensor matrix product. And if we materialize it in one direction, say the third direction, we will obtain a matrix with dimension P3 by P2 times by P1 times P2. And you can see that the left singular subspace of this matrix has some information of M3. So we can directly try to do the SVD on this materialization. But we cannot directly work on this UK tutor, say doing K-means or doing what we do in the spectral clustering. The issue is that when you are doing this kind of matrix SVD, you do not fully utilize the structure of the tensor structure. That means you do not utilize that you have the two clustering structure in another two directions. So we do not cluster it right now. Instead, we do the projected SVD. Because we have this UK tutor, although it's not a perfect estimation of the subspace, it can be like a preliminary estimation. So we project the raw data Y on this preliminary subspace, and then we do a singular value decomposition once more. And we obtain this U hat as a better estimation. Then we project the raw data on this three projected subspace and obtain the low dimensional loading, and we perform K-means on this data. So I have a pictorial illustration which might be more straightforward. We have the tensor Y, and we first materialize it, and we do the singular value decomposition. We have a preliminary estimation of the subspace, and then we project the huge tensor on these two subspace. We obtain a smaller tensor, and then we do the similar materialization and SVD. We obtain a better U3 hat. And finally, we project the whole tensor onto the three directions and obtain the low dimensional loading, and we project the clusters as loading. So in the right, we have the scatter plot for this 8 entries as loadings. We can see that in each step, the two groups are actually more separated. That means actually this stepwise refinement increase accuracy for the clustering. And in the rest of the talk, I will focus on the theory of the model and our method. To start with, I would like to introduce some preliminaries. Our assumptions are very simple. We just assume that our noise are independent mean zero sub-Gaussian with sub-Gaussian norm sigma. And we also consider a simple case where each mod has balanced clustering in this sense. And we introduce the following misclassification rate. That is, given Z1 and Z2, we calculate the misclassification rate up to the permutation of the clustering. And in our theory, we will evaluate the clustering performance based on two matrices. One is a consistent. We see the Z hat is a consistent clustering for Z if the misclassification rate of Z hat with respect to Z converts to 0 in probability. And we see that this Z hat is asymptotically exact if with probability going to 1, that the misclassification rate is 0. Then we would like to ask, what is the condition for successful clustering? And you can imagine that intuitively, significant separations between block means are preferred. So we denote this delta K as the mod K slice separation, which is defined as following. So basically, this delta K evaluates the minimal difference between two matrix slices from two clusters in a specific mod K. And we define the signal to noise ratio as a ratio of sigma mean square over sigma square, where delta square over sigma square, where this delta sigma is a sub-Gaussian norm. And here I want to make two remarks. Firstly, we really need the delta square to be greater than 0, as it's a sufficient and necessary condition for the model identifiability. And also, we can expect that if we have a stronger SNR, then it will make the clustering statistically easier. Now, we are ready to present our theoretical guarantee. Our first theory concerns the consistency of high-order spectral clustering. For simplicity, I will just assume that all the tensor dimensions have the same order and all the tensor clusters have the constant number. And if we denote this CK0 as the initialization from high order spectral clustering, then we can prove that with high probability, the misclassification rate is bounded by this rate. And for a quick conclusion is that we can find the sufficient conditions for either consistent or exact clustering. Remember, for consistent clustering, we just need this upper bound to converge to 0. So we just need the SNR to be much larger than p to the power of negative half of d. And if we want it to be exact, we need to add another additional power of 1. So the question is, can we do better if we further apply the high order Lloyd refinement? And the answer is positive. Here comes the local refinement of high order Lloyd. We assume if we have fit this algorithm with some initial clustering which are consistent, and we have this signal to noise ratio, then with high probability the clustering result will be exact, as long as we have sufficient iterations which has a logarithm of dimension p. So combine these two theorems, we can conclude the sufficient conditions for exact clustering, where we require the SNR to be much larger than the p to the power of negative half of d or p to the power of 1 minus d times log p. If we ignore the log term, then we can see that when d equals 2, which reduces to the matrix block model, we just need the signal to noise ratio to be p inverse. And if d is greater than or equals to 3, we need the signal to noise ratio to be negative half of d. And this rate is very important, which we will revisit it shortly. So the next question is this SNR condition we applied really necessary? To answer this question, we need to establish some statistical limit, and we consider the following general parameter space, and we are able to prove the following statistical error bound. That being said, okay, if this signal to noise ratio is bounded by p to power of 1 minus d, then it's impossible to have an exact clustering. Here, the infimum is taken over all the possible estimation procedure. So if we combine these two results, we can obtain this phase transition figure, in particular in the left panel, which we have d equals to 2. Because in that sense, the sufficient condition, which is negative half of d, is equivalent to the necessary condition, which is p equals to 1 minus d. So we close the gap. That being said, in the region A, our algorithm is statistically optimal, but in the region B, it is statistically impossible to do the exact clustering. But if we consider the tensor case when d is greater than or equal to 3, we find there is a gap. We are only able to characterize the region A and B, but we have no knowledge about this region C. So for this, we need to first argue whether this lower bound is optimal. To answer this question, we revisit the constraint MLE. And it was actually shown by the previous work that when the SNR is much larger than this rate, the MLE achieves exact clustering. That means the MLE is actually statistically optimal as it matches the lower bound. And this p to the power negative d minus 1 is the statistical limit for exact recovery. But as we just mentioned, the exact computation of MLE is difficult or NP hard. So we may next ask, how about we restrict our attention to all the polynomial time efficient algorithms? To answer this question, I would like to first introduce the following hypergraphic planet click detection problem or hypothesis introduced by Rungang Han in their 2022 annals paper. Basically, they have established some hypothesis with many strong evidence, and under this hypothesis, we can develop the following computational lower bound. That being said, if their proposed HPC detection conjecture is right, then we can prove when as long as the SNR is smaller than this rate, then it's also impossible to identify the to make the exact clustering when we only consider the procedures that take polynomial times. So if we utilize this result, we can now fully characterize this this phase transition in our tensor model. That means is when we are at the strong signal to noise region A, we propose a method which is polynomial efficient and it can achieve exact clustering. And when we are at the signal to noise region B, the MLE can achieve optimality. No, when we are at the region B, no algorithm can achieve the exact clustering. When we are at the region C, we have already shown that MLE can achieve optimality, and we also show that there is no polynomial algorithm can achieve the exact clustering. So that figure tells us the trade-off between statistical optimality and computational efficiency. And we use some numeric results to verify our theoretical understanding. So basically, we implement our proposed method and also an oracle procedure. So the oracle procedure is implemented by running the high-order Lloyd optimization from initialization, which is a slight perturbation of the ground truth. We use this oracle procedure to approximate the MLE. And you can see from these two panels, in the left panel, these two algorithms have the same transition borderline, which is gamma x to -1, which is essentially negative half of p. But in the right panel, when we have the order 3 tensor, the two procedures have different transition borderline. And it actually matches our theoretical rate for both transits to the different region. And because I think I still have maybe three minutes, I can briefly review some technical contribution of this work. So basically, in our analysis, although we want to bound the misclassification rate, but it's in general technical difficult to deal with, as it involves this indicator function. So we introduce the following auxiliary measure, which quantifies the actual loss from the misclassification, and we can establish the equivalence between this HK and the LK. And all our analysis is performed on this LK. And to prove the high order spectral clustering, we note that if this Z10 is a cluster outcome of this K-means on this Y1 hat, which is 2 times projected matrix data, it is equivalent to applying the K-means on the row of the original high-dimensional data after you project the data back. And we can simply prove that, okay, this L1 is bounded by the estimation error of Y of the X after we do the projection. So the central problem will become bounding the tensor estimation error. And it has been proved by a previous work by John and Shah in 2018. That is, if we have one tensor which can be written as a signal tensor with low rank plus some noise tensor, and if we have some least singular value lower bound, we can establish this estimation error. But this result cannot be directly applied to our model, because in the multi-way clustering model, we can have some degenerated singular gap. For example, if we consider a cotensor with this form, we have the rank or we have this cluster number equals to 2, but this tensor only have rank 1. However, in our assumption, this model is still identifiable because the minimal slice separation is positive. So to address this issue, we develop a new tensor estimation bound, which is free of the singular gap. In this proposition, we do not even need the singular gap to be greater, the least singular value to be greater than 0. We have this singular gap free bound, and this bound can be directly used to our purpose. And just a quick summary, we studied the multi-way clustering problem under tensor block model, and the algorithm we proposed are the high order spectral clustering and high order Lloyd algorithm. And we study the statistical computational limits, the phase transition, and we can also provide the tensor estimation under the model, although I didn't show it. And we also actually do several applications, including the flight route, the air flight route network and the time-dependent recommend system. And in the future, it is very interesting to model the multi-way clustering structure under other statistical assumption structure, such as the non-Gaussian data as binary or count, or we can introduce the sparsity to model the important features, and we can also introduce the continuity to import to model the time-dependent structure. And this paper is currently under revision of GISS Series B, and the preprint is available on arXiv. And that's all. And thank you for your attention. And I would also like to thank IMS for this wonderful opportunity. And I would also like to say thank you to my PhD advisor, Professor Andrew Zhang, for his exceptional mentoring. And I'm happy to take any question.
Okay, Rungang, thanks a lot for the wonderful talk. Any question from the audience?
One quick question.
Sure.
So I was pretty much interested in the future directions you mentioned. I was just curious that whether you have run any simulation study to see the effects, like whether there exists a computational statistical trade-off in kind of binary outcome model or something like that.
I'm sorry, I cannot hear you. Are you asking about the simulation? I can just hear several words. Say it again, or Yushin, can you
move to the future direction slides where you mentioned a few things?
Yeah.
Can you say again what?
So I was wondering that whether have you run any simulation studies with the non-Gaussian data, and whether such statistical computational limits you have found in that setup also, because that's very interesting because it kind of relates to hypergraph SVM. So
yeah. Yes, that's a very good question. So actually, one very interesting question is how to series study it under the Bernoulli noise or the hypergraph. So currently, we assume that the epsilon means there's Gaussian. So in general, if you are dealing with a dense graph, you can actually apply our results, and all things still holds as long as you treat this Bernoulli distribution as sub-Gaussian. But the more theoretical interesting work is to consider when you have a sparse graph and the connecting probability tends to 0. In that scenario, I guess, firstly, we need to define a different signal to noise ratio, because in the Bernoulli model, you don't have a separate separation, mean separation and the variance. They are all characterized by the connecting probability. And also in that work, we have theoretically investigate what will happen here. Basically, our iterative algorithm still work, but the initialization algorithm may not work well, because in the sparse hypergraph model, we believe that even the spectral method may not work really well, even in the matrix case. And in terms of the simulation, we have in our paper, we have to do the simulation by applying our method on the Bernoulli case, but we do not study the similar phase transition. This is under the Gaussian noise.
Thank you. I also have a quick question for you. So, so you have one slide that says if you only run the I don't know how you call it, high order spectral algorithm or whatever, and you said this, if the SNR exceeds something, you get consistent estimation. If SNR is further larger by a factor of P, and then you get exact recovery, right? So,
yeah. That's
yeah, so this one, yeah. So I'm just a bit curious, because in the non-tensor setup, in the standard SVM, we know that the spectral method for either consistent or exact recovery, if you can just run spectral method, do rounding, and then you get everything. You don't need an additional factor of P. You don't need refinement actually in So
yeah, that's a very good question. So we actually also thought that maybe the high order clustering already achieves the optimality, but the issue is that we cannot. So if we directly analyze this, the bound from the HAC, basically we can just obtain this dependence, the polynomial dependence on the SNR. But in the high order Lloyd, we are able to obtain the exponential dependence on the SNR. So if we only have this, the inverse of the SNR as a upper bound, then you have to increase the power of P to make this rate to be even lower. But if we can, obtain, say, the bound is bounded by the exponential, say, negative SNR plus, times blah blah, then we can then the rate for the consistent and exact are the same. We are not sure whether this scenario, this theory that holds in matrix also applies to tensor, but currently we cannot prove that. We can just add another iterative procedure to further guarantee this. Yeah.
All right. Okay. Thanks. Any further question? All right. If not, let's thank Rungang again, and also thank all the 3 winners.